Okay, guys, so we've gone through how the heating curve stuff works, but now what we need to do is spend some time practicing it, okay? Really, there's not a lot to this. It just takes some time to work through different possibilities and make sure that we take this thing, break it down step by step by step, okay? So if we were in class, we'd be doing this together, but we are not, so here we go. Here's our calculation. How much energy is required to heat 10 grams of ice at 0 degrees Celsius to liquid water at 50 degrees Celsius? Now, before we go any further on this problem, I really think it's important that you take a second to diagram out what's going on here, okay? So let's kind of take a little diagram here. It says I have 10 grams of ice, all right? So my mass is 10 grams, and I'm dealing with ice, which is an information that's very useful for me, okay? And it's at 0 degrees Celsius. So if I'm going to diagram this, I'm sitting right here. I am ice, and I am a solid because I am ice, okay, at 0 degrees Celsius. Now I want it to become a liquid water at 50 degrees Celsius, okay? So the reason why we spend that so much time talking about it being ice and being a solid is because where are we at on our heating curve, okay? If I'm here and I'm a solid and I'm ice, that means I have to melt first, okay? So I got to melt. Then once I melt, then I can warm up, okay? So I have to go through this process first as step one, and then I have to go through this process too as step two, okay? So I have two legs to my problem here that I'm working with as I do it. Now, this is 0 degrees Celsius here because I'm dealing with water. This is still 0 degrees Celsius, and then we're looking for that endpoint, which is going to be 50 degrees Celsius, okay? Now, I took a lot of time to set this up, but when you're doing these practice problems and working through this, this is the part you want to do first and do it very quickly, but kind of in your brain say, okay, where am I at? Where am I ending? Because now you've framed the problem. So we now know that we have two steps to go through. We now know that each step is a little bit different, so we can pick the right equation to solve for it, and we can work through that process, okay? So we're going to work our way through this. Now, to do this, I need to know that something is melting, right? So my energy change, okay, or my Q value is going to be my heat of fusion here because I am melting, okay? Now, that means it is melting, so it's absorbing energy, so this is going to be positive, all right, times my moles, okay? My part two is going to be an MCAT, okay, scenario here. Now, keep in mind, remember, this answer gives us up in kilojoules. This answer will give us things in joules. So let's make sure that when we're done and we take part one and part two and we add them up, that we're either both in kilojoules or we're both in joules when we add these up at the end, okay? So let's make sure that we are conscious of that as we're working our way through this process also. Those are the things I got to think about before I actually can start plugging numbers in, okay? So other thing I need to know, well, I need to know my values, okay? So I'm dealing with ice right here. Now, ice has no value to it because ice is the same as water. The only thing that we need for ice is its specific heat capacity because it is different than water's specific heat capacity, okay? We know the melting point. We know the boiling point, which we want to deal with. We're not vaporizing, so we won't deal with this. So we're going to deal with this number for our heat of fusion, and we're going to make it positive because we have a melting process here, okay? So we did a lot of setup. So now it's your turn to finish this thing off, okay? Use our two equations. Find the value for the melting stage, part one. Find the value for the warming up stage, part two. And then once you're ready, I'll show you the solution. Okay, so go ahead and pause the video here, solve it, and then come back to me. All right, so here we go. If we take a look at our process here, first thing we did is we converted our grams of our water to moles because we needed moles here. Here's our equation, took our moles times our moles, and we get 3.34 kilojoules, okay? That was just needed to melt, all right? Now, second leg of this thing, we had to warm it up from 0 to 50 now. So we took our 10 grams, specific heat capacity of water. We went from 0 to 50, so final minus the initial, because it was warming up. Again, it should be positive. This is in joules. I converted to kilojoules, and then I add the two together, okay? I will promise you, the most common mistake that I see on this is not doing this, it's not doing this. The most common mistake I see is converting at the very end, because this problem, because specific heat capacities are done in joules, you get an answer in joules. It's every year it happens to me. So make sure at the end that you're keeping track of when are you in kilojoules, when are you in joules. All right. Now, final step here is we add the two together. So our final answer here. Whoa, sorry about that. That one kind of fast. Let's do that again. Our final step here is to add them up, and if we do so, those who add together give us 5.43 kilojoules of energy. Right? So we now know the energy it takes to melt it and to warm it up to 50 degrees Celsius if we had 10 grams of water. Right? That is probably about as easy as these problems get. Okay, they can't get much easier than that, because if it was a single step problem, it wouldn't be worth doing all this extra work. Okay, so keep in mind that problems can get more complex as we work our way through. Okay. In fact, one of the complexities that we get is what happens if it's not water, okay? So can we still do this if we're doing something that is not water? Absolutely we can. Okay, so let's take a look at this from the perspective of ethanol. What's the energy change when 35 grams of ethanol is heated from a liquid at 50.7 degrees Celsius to a gas at 93.5 degrees Celsius? C for ethanol vapor is not in your chart, it is this, okay? So we know ethanol's specific heat capacity as a liquid. We don't know it as a vapor, so I'm providing that information here. All right. Again, let's set this thing up and see where we're at. So we have 35 grams of ethanol right now, and we are starting at a liquid at 50.7 degrees Celsius. So I'm at 50.7, and I am a liquid. Now, it's going to warm up to the point at which it boils, okay? And then it has to boil, and then it's going to have to heat up to a final temperature of 93.5 degrees Celsius as a gas, okay? So I need to do a little bit more investigating, because I don't know this point here. What is that flat line? Is it 93.5 and I really only have two legs? Is it 50.7 and I only have two legs? I just don't naturally know what ethanol's boiling point is. All right. So I need some more information. I need a table. Oh, good. Look, I have a table. So if I look here, there's ethanol. Ethanol melts at negative 114. Ethanol boils at 78.4 degrees Celsius, which means my flat line here is 78.4 degrees Celsius. This is this value here and here, because it does not change temperature when it boils, okay? So now I know in part one, I have my starting temperature and my ending temperature. Part two, I'm going to be taking, and I'm going to be finding my heat of vaporization for ethanol times my moles. And in part three, again, I know my starting temperature and my final temperatures. So parts 1 and 3, I'm going to be using MCAT. Right? Again, keep attention to that C value, because the C value for 1 will be different than the C value for 3. So let's take a look at that. Okay? So for 1, our C value is a liquid. So the values on this chart, the specific heat capacities, are those values at room temperature. Okay? So ethanol is a liquid at room temperature, so this 2.44 only affects ethanol as a liquid. Okay, so at part 1, it's 2.44 joules per gram degree Celsius. At part 3, that C value was given to you in the problem. So we go over here, we said it's 1.65 joules per gram degree Celsius. So now that is 1.65 joules per gram degree Celsius. Okay, so we have our C for part 1. We have our C for part 3. Heat of vaporization, we need to look that up. So here's ethanol, and we work our way through, and heat of vaporization is 38.7. Again, we are boiling, so it is going to become a positive value. So we know that that is 38.7 kilojoules per mole. as we do this, okay? We have everything set up. Now it's your turn, okay? So you know the C values, you know the heat of vaporizations, you know you have a 3-step process, and now it's time to work it out, okay? So once again, please pause the video, put the equations in, add everything up, and come up with an answer, and then unpause the video, and we'll get to a solution. All right, here we go. So we have a 3-step process here. And with that 3-step process, first thing we want to do is take a look at Q1. So in Q1, we had 35 grams. We had a specific heat capacity of 2.44. Our temperature change was from the boiling point from its original temperature. We got a Q1, and then I instantly converted that to kilojoules because I know that I'm going to need this stuff in kilojoules at the end. For part 2, I had my my molar heat of vaporization. I had my mass in grams, so instead of doing it as 2 steps, I said, well, this value is grams over molar mass to moles. That is basically the math times this will give you my answer. So I started combining my work a little bit here. And doing that, I got 29.4 kilojoules. In part 3, I'm back to the grams or the mass again. I have my new specific heat capacity for a gas of ethanol now. I went from 93.5 to 78.4 as my temperature change, and I got 0.872 kilojoules. I added those things all up, and I got 32.6 kilojoules of energy change for this to happen, okay? There we go, all right? So 2 practice problems, one with water, one with ethanol. I worked it through with you guys in terms of like the setup, drawing it out, kind of mentally preparing yourself to do the math, okay? I truly believe if you jump right to this, you're gonna make little mistakes because it's not one quick little equation. It's combining 3 equations together, converting, using mass in some places, using moles in some places, different C values. There's a lot going on to set the thing up. So take the extra 3 seconds, 5 seconds, 10 seconds, 4 minutes, whatever it takes you to draw it out like I did on the iPad, to identify my C values and do that. I promise you it'll create a much easier scenario for you, okay?